All right, guys, we are going to go ahead and do a couple more practice problems with stoichiometry and molar ratios. Go ahead and take out periodic tables and your molar map, as well as a calculator to work through these problems. Feel free to pause the video whenever you want to try something on your own, or you can rewind if you need to rewatch something or try something on your own again. However you think these videos will be the most helpful for you to work through these problems and be the most beneficial. So here's our first problem then. We have a balanced equation, and our problem is asking us how many milliliters of a 0.309 molar solution are produced from 2.40 times 10 to the 22nd molecules of H3PO4. This is an instance where we have two givens here. I have the number of molecules of H3PO4 as well as the molarity of a solution of NH43PO4. This is a situation where you're going to look at the two givens and choose the given that you can put over 1. Not over 1 in a unit, just 1. So if we look and we know that molarity is moles over liter, so this one is not going to be something that we can use over just 1 because there's a unit. So we will go ahead and start with the 2.40 times 10 to the 22nd, and that is molecules of H3PO4. We can just go ahead and throw that over 1. When we start our next equivalent statement then, we know that molecules of H3PO4 has to be on the bottom so that our two units can cancel out. And we know from our molar map that it is Avogadro's number of molecules in 1 mole of H3PO4. Our next equivalent statement then, we're going to have moles of H3PO4 in our denominator because we need to cancel moles out with moles of H3PO4. And if we look at our balanced equation where our coefficients are, in front of H3PO4 is a 1. So we know that it's going to be 1 mole of H3PO4, and on the top we're trying to get 2 moles of NH43PO4. And based on our coefficient here, we know that that is a molar ratio of 1 mole of NH3PO4 to 1 mole of H3PO4. Our units cancel, and we're trying to get, it's saying how many milliliters. So this is where we can use our molarity, and we will write that 0.309 moles of NH43PO4 are in 1 liter of that solution. Because remember, when we have something, I'm going to go ahead and draw this down here. If we have something that's 0.309 molar, we know that that's also 0.309 moles per 1 liter, or we can always write that as 1 liter over 0.309 moles, because that's just a ratio of how many moles are in every liter. Whether you write it how many liters, 1 liter, for how many moles, or this way, it doesn't matter. All right. I'm gonna go ahead and erase this down here so we have a little bit more room. Okay, so then we have our moles of NH43PO4 canceled out, and we are left right now with liters of solution. So our last step, and I'm going to draw this over here where I have a little bit of room left. We know that for every liter of solution, 1 liter of solution, there are 1,000 milliliters of solution. And if a problem is only asking you for volume up here, then you wouldn't have to write this, but our problem is specifically saying milliliters. So we can cancel out the liters of solution. And when we plug this into our calculator, we would get 128.977 milliliters. But we know that that answer is incorrect because we have not taken into consideration the number of sig figs. Both of our givens up here, both of these numbers, have 3 significant figures. So we would round this number up, and our final answer would be 129 milliliters of NH4 3 PO4 solution. And then that's it for that problem. If you chose to just write the NH4 3 PO4, or if you just chose to write solution, either one of those are fine. I'm just choosing to write both of them to reiterate that that is a solution of the NH4 3 PO4. All right. For our next problem here then, we have another balanced equation at the top. And our question is asking us how many grams of C10H22 are needed to react fully with 2.30 times 10 to the 24 atoms of oxygen gas. We only have one given for this one, so it's pretty easy to know which one we're going to start with. So we will write 2.30 times 10 to the 24th atoms of O2, and we'll go ahead and throw that number over 1 to make our math line up throughout. When we write our next equivalent statement then, we know that we're going to have atoms of O2 on the bottom so that these units can cancel out. And if we take a look at our mole map, we know that we can go from particles to moles using Avogadro's number. And in this instance, we cannot go directly from atoms to moles. We first have to go from atoms to molecules to moles. And that's because Avogadro's number is the number of whole things in 1 mole. And in this situation, the molecule is our whole thing. So that being said, our first thing we'll do is say there are 2 atoms of O2 in 1 molecule of O2. And we got the 2 from counting O plus O. So there are 2 atoms there. Our next equivalent statement then, we know molecule. Oops. Hang on 1 second. There we go. Let's erase that, and we know that we need molecules of O2 in our denominator so that these units can cancel. And this is where we can now use Avogadro's number and say that there are Avogadro's number of molecules in 1 mole of O2. Our next equivalent statement will then have mole of O2 in our denominator, and we're going to use our molar ratio to go to moles of C10H22. And to find that molar ratio, we look at our coefficients up here. So we say that there are 31 moles of O2 react with 2 moles of C10H22. Our moles of O2 now cancel out, and if we stopped now, we would be in moles of C10H22, but I'm going to go back down here. This is asking us for grams, so we will do moles of C10H22. And we will do 1 mole of C10H22 and then find the molar mass. So C10H22, that molar mass, which we get from the periodic table, is going to be C 12.01 times 10 plus H, which is 1.01, times 22, and that will get us 143.32 grams per mole. So up here we can write 143.32 grams of C10H22 are in 1 mole. Our moles cancel out, and I'm going to go ahead and write our final answer in a different color here. That will get us 17.657 grams, which we would round to 3 significant figures to become 17.7 grams of C10H22. All right. Okay, for our last problem here, we have an unbalanced equation at the top here. Go ahead and pause the video and take a second to try and balance this one. All right, now that we have the equation balanced, I went ahead and put that up at the top here for you guys to take a look at. You can check yourself on if you balanced it correctly and then try and work through the problem now on your own, and I will write everything out so we can go over that in a second. All right, so I went ahead and put all of the work written out here, although we don't have a final answer yet. We'll go through each step though. We start with the 1.90 grams of N2. That was our only given, so we only had one option as to how we would start. I went ahead and just threw that over 1 to make our fractions all line up and make our math look good. Our next equivalent statement then, needs to have grams of N2 on the bottom, so these units can cancel out. And we can calculate the molar mass of N2 by doing 14.01 times 2, and that gets us 28.02 grams per mole. We used that up here in this statement, and now we're left with moles of N2. We know we have to write moles of N2 at the bottom in our denominator in this fraction. And from our coefficients here, we know 1 mole of N2 reacts with 2 moles of RbNO3. And that's how we got this top half right there. Our last equivalent statement then needs mole of RbNO3 on the bottom in our denominator, so those two can cancel out, and we calculate the molar mass of RbNO3 by saying Rb, which is 85.47, plus N, which is 14.01, plus O, which is 16 times 3, which then gets us 147.48 grams per mole. We use that fraction up there, and we are left with grams, which is our final unit. I'm going to go ahead and erase all of this. We have a little bit more room. And when we plug this into our calculator, then our final answer is going to be 20.001 grams. We need to round to 3 significant figures, leaving us with 20.0 grams of RbNO3 reacted.